objects in the environment and infer what's going on in the environment. And then it's also running high-level control, so the sort of MDP style. It isn't exactly using MDP, but you can sort of think of it as that way, like integrating all of this input and then deciding what actions to take in response to what people are doing. So it's very, as you can imagine, it's a very challenging problem to make these robots do interesting things. And there's a lot of ongoing research in that area. It's one of the grand challenges of artificial intelligence. And if you're interested in learning more about it, we have whole classes about robotics. So Chad teaches one, Michael's going to teach one joint, Michael Littman's going to teach one joint with RISD next semester about the sort of hardware and design side of robotics, and Chad teaches one that really focuses on what we know about sort of particle filters and things like that, algorithms for making robots do things. So today we're going to talk about sort of one sub-problem of robotics, which I've spent a lot of time thinking about, which is how do we tell robots what to do? So how could we tell? So these are different robots. There's a forklift again, the quadrotor helicopter can fly around. It's a flying robot, it's really cool. It can fly around in indoor environments. This is a robot built by undergraduates. The vehicle wasn't, but the robotics pieces of it was at Olin College. And it can, like the forklift, it can drive by wire, it can drive autonomously, it can avoid obstacles, and it can follow missions through the environment. And this is a PR2, so that's the same robot we have downstairs in the robotics lab at Brown. It can pick things up, it can put things down. It's got a LiDAR sensor here that rotates up and down so it gets sweeps like this. So it gets sweeps. It's got stereo vision, so its head is nice and wide, so it can take these two cameras and diff the images and get like a 3D point cloud from it. Our PR2 has a Kinect mounted on the ceiling. Everybody know what a Kinect is? I think there was this question before. Some of you don't. So a Kinect is a camera, so you get RGB, and it's augmented with an infrared sensor. So it bounces infrared light out at the world and measures how long it takes to return. And it uses that to figure out how far away stuff, as long as it's not like a glass, like something that doesn't see infrared light. But how far away stuff is in the world. So for each pixel you have red, green, and blue, and you also have depth information. How far away that pixel is from the sensor, the Kinect sensor. And this was a sensor developed by Microsoft for video games, and it's used to play things like these sports games where you can actually like swing a tennis racket without actually swinging it, and it figures out like where the ball should go in response to that. And everybody's putting them on their robots now because it gives you a lot more information than just computer vision with just pixels. It gives you about the environment. So, question? Okay. So we're trying to figure, what I think spend a lot of time thinking about is how do we tell robots what to do? And how can robots figure out what to do so that they do things that help people? So they do things we want them to do and not things that we don't want them to do. So how do you guys think we should tell robots what to do? Yes?
You could like have a set of commands it knows how to reply to, or like
yeah, a fixed vocabulary of commands. Great. What else? What else can we do? Yeah?
You could have a kind of programming language that
Yep.
gives it like policies in a sense, but sort of at a higher abstraction level than like a specific policy of how to control the motors. Like a
Right. So you could
abstract
have low
policy.
level, and you could have high level. Yeah. So like assembly language, or you could all go up to like, Python or higher level than that. Good. Yes.
You obviously need to translate into one of these, but have some sort of computational linguistics that, tries to understand.
Understand natural language.
Yeah.
Right. So we'll call that natural language. So like as produced by an untrained user. What else? Yeah.
Maybe not possible yet, but sending it an idea from your mind of something.
Oh,
you
cool.
want.
Yeah, mind control. No, people actually do that. So especially in rehabilitation robotics, there's a lot of work on putting things like these helmets on your brain that look at the signals. And also in animals, they actually stick stuff in your brain. They actually put wires directly talking to your neurons. And then if you think a certain way, the robot can actually move. And this is really exciting for people who are paralyzed or they have some kind of injury, because the potential is that they can control a robot arm and a piece of assistive technology just like you control your arm. You think, and somehow my arm is moving in particular ways. So it's very exciting new technology that actually has been demonstrated. Like a monkey, I think it was across the country, a monkey in California controlled a robot arm in Boston. A year or two ago, there was a newspaper article about this. That actually happened. Like they actually put a wire in the monkey's brain and it successfully moved the arm across the country using mind control. I think it's science fiction. It's not. What else? Yeah.
Yeah, like using your body. Like if you move your arm, it'll do something. Like some command.
Yeah. So like imitating body movements. So if I lift my arm up, the robot should lift its arm up. And this gets a little tricky. Like, what does that correspond to with the forklift? Like, if I go like this, should the mask go up, or like this? There's some. PR2 is kind of humanoid, so maybe my arms should kind of correspond. But even that's different because it's got some number of joints, and the degrees of freedom, the ways that its joints move, and the ways that my joints move are very different. And so you can imagine some kind of mapping, but maybe you really want to worry about the end effectors. Like maybe what really matters is that my end effectors are in the same pose, regardless of how its arms actually got there. Let's just get my arms there. Another interesting piece of this is sort of the feedback of it. So like, do you get to watch a video of the robot doing this, or are you in the same space as the robot to control? There's also some very interesting work on force feedback. So like, this was work when I was visiting Penn. They showed me this little glove that you put on your hand, and then you open your fingers, and the PR2 grippers open, and you close your fingers, and the PR2 grippers closed, and it had force feedback. So if you close your fingers around an object, you could feel the force pushing back on your fingers through the glove, like it was pushing on your fingers, so that you could tell that you actually picked something up to do teleoperation. So again, very exciting area. A lot of people are thinking about different ways of sort of mapping body movements to robotic movements. What else? There's one more that's used all the time. Maybe it's almost too obvious that I'm kind of fishing for. Yeah.
Voice?
Voice is, yeah. I mean, so voice could any of these could be voice. I'll write it down though. I think it's good. What if I didn't want to, like, maybe less AI? Like what's something easy I could do? Yeah.
Like keyboard.
Yeah. Right. It's keyboard and mouse. Keyboard. Mouse. Or a lot of people use like gaming controllers, like joysticks. The PlayStation controller has a venerable history in robotics. And actually today, if you want to move our PR2 around the lab, you don't tell it what to do. You pick up the PlayStation controller and you associate it with the robot, and then you drive it around with the joystick. And that's how you make the robot move around. And a lot of the work in Chad's lab is focused on, I'm sort of saying keyboard and mouse is easy, and in some ways it is, because making a bad interface is pretty straightforward. You can have a little slider that maps to the joint angles of your arms at the lowest level, and then you're kind of adjusting the slider, and the arms are going to move, and they're going to move exactly where you say they're going to move. But it's pretty laborious to do that. It's pretty difficult to actually move the arm in where you want it to go using these types of keyboard interfaces. And one of the things that Chad's working on is trying to come up with better ways of enabling a person to control a robot using a keyboard and mouse or a PlayStation controller by integrating autonomy in the right way. So ideally it would just all work autonomously, but in practice our systems are never quite as reliable as we want them to be. So then the question, I think a really interesting user interface question, which is when do you let the person control, what degrees of freedom do you let the person control, when do you let the autonomous system do its thing, And how do you make that trade-off so that overall the system is better than it would be on its own? Does anybody else have any other things they want to share? That's sort of the main modalities that I've seen people use. But it'd be interesting if there was others that. Yeah, Karthik. Oculus Rift, good one, yeah. So, do you want to say what the Oculus Rift is? Karthik?
So it's like the goggles, like one you wear so that you see what robot sees. And I don't know how they operate. Like maybe they have some
Yeah.
plastics or something. but-
Yeah. So it's like virtual reality, right? Like you put these 3D goggles on, and then you can be the robot, and you can see exactly what it's seeing, or you can at least see what its sensors are seeing, and that might give you better. People say it makes them dizzy. I haven't actually tried it yet. People say it makes you dizzy, but it might give you better control or better information about what's going on in the robot's environment. Thank you. All right. So we can here's some pictures of some of the existing interfaces. This is focusing mostly on these last two, so keyboard and mouse, joysticks. So this is showing the iRobot PackBot. This is a robot that's used in Iraq and Afghanistan to disarm improvised explosive devices. So they send the robot in instead of sending a person in where they think there might be a bomb in order to protect the safety of the soldiers. And the way that they control this robot, this is an older version of their interface. It's like this big clunky looking joystick. Their newer technology actually uses an actual PlayStation controller. And it's really nice because they can just hand it to a soldier, and if they've ever played PlayStation, they know exactly what to do, what the degrees of freedom are, and how to control it, and they can be driving the robot in 10 or 15 minutes to make it do stuff. This is a similar kind of interface developed for the forklift. So this is using a tablet device, like a cell phone. And this is an example of integrating autonomy. So the PackBot, these robots have to use pretty low-level control. So you're using the PlayStation controller and you're using very low-level movements. You're directly controlling joint angles or joint velocity. And you're watching the robot to sort of see what it's doing. So it's like driving an RC car or something like that. With this interface, you're giving the forklift much higher level commands. So here what he's going to do, or what he does, is he circles a pallet in the environment, and he says, click the pickup button. And then the forklift goes off and has a little MVP or little controller that runs through the policy for picking up the pallet. So it knows how to drive close to it, and then it has this little alignment process where it lines up its forks with the pallet, it drives a little closer, it'll like kind of correct itself, and then it'll pick up the pallet and then drive back a little bit to sort of make sure that it picked it up. And then if you want to put it down, you circle a spot on the tablet where you want it to go, and it'll do the same thing. It'll put the pallet down in a different location. So you have this hybrid between giving it low-level commands and or sort of high-level commands and autonomy in the same system. This example is another one that's sort of there's a lot of military applications for robots, but this is used to control drones. So another application of military robots is drones to go out and do surveillance, that sort of fly and take video of what's beneath them in order to gather intelligence about what people are doing out there in the environment. And what's interesting about this interface is first of all, you got to have this big backpack on, but second, to see what's on the screen when you're out in the field with the bright sunlight, he's got to wear this hood. So that he can see the screen of what the robot's seeing and doing and what he wants the robot to do. So his hands and his eyes are focused down at the screen rather than out at the world where interesting things might be happening and where you sort of want things to go. So you can sort of see that, like if we made this list, there's kind of a spectrum in these different control modalities. Sometimes there's some applications where some are good and some applications where others are good, and there's for sure a trade-off between reliability and stuff. So if you're using this PlayStation controller, you're directly controlling joint angles. There might not be very much autonomy, but it's pretty hard to mess it up. Like you might mess it up, but you're not going to have your program kind of freeze on you or something like that because there's just very little software that's going on there. Whereas when you have these more autonomous versions, it might, and we've seen this happen with the forklift, like it might fail because the pallet wasn't heavy enough and it didn't trigger the sensor on the forks to indicate that it's actually picked something up. And so then the whole thing goes kablooey. It doesn't actually explode, but like it doesn't work. It doesn't pick something up that you wanted it to pick up. So instead, what I think about in my research over the past 5 years or so is how we can make robots this one right here. How can we make robots understand natural language? So if you say something to the robot like return to Camp Charlie and take the eastern path to the landing zone, then you want a robot like this one to infer a trajectory through the environment that it should follow, or a sequence of actions or a policy for its MDP controller to correctly follow that natural language command. So see what this looks like. I'm going to show you a video. I think I've shown this one before, but this is a helicopter following commands.
124, then face the windows and go up.
So here it's using speech recognition on the iPhone, so like a voice interface. Then we run the inference. So this is actually running a particle filter data localization in the map, just like what you guys made. And then it infers the trajectory through the environment. And then it gets sent off to the robot to be executed. So this is its view of what it sees. And this is its particle filter running as it's moving through the environment. So you can see this is just from the best location, like where it is in the environment based on the LiDAR scans. So here it's flying through, it's turning so its camera faces the window. In a second. There's a LiDAR in the front. With a mirror to reflect the beam down so they can get a height estimate, and then gets a shot through the windows that you're going to be able to see. So, we also did this with the forklift. So here with a robot like the forklift or like the PR2, you don't just need to move yourself through the environment, you also need to change the environment. So you have to figure out what the pallet is, what the truck is, and then what actions you're going to take that's going to cause the pallet to be on the truck if you're going to follow this natural language command. So this is kind of it's a very AI-y, I don't use AI as an adjective, it's a very AI-y kind of problem because it's integrating a lot of different stuff. We have to do perception to know what's out there in the environment. We have to do some kind of MDP kind of control to figure out what actions we should take. We have to do natural language understanding to figure out the policy for our MDP in terms of the words that people are saying to us. And doing all this mapping is really hard. So what we always do is, like when you have really hard problems like this, is you find some slice that you can get your head around. And what we'll talk about today is sort of different slices that we've looked at in this area. So this is actually a very old problem. This idea of mapping between words and language and stuff out there in the environment. So this is sort of one version of it. If you say the pallet of boxes on the left, and you have a picture that the forklift took using its camera, somehow you have to go from these words to these pixels, and that's a sort of one subproblem of this, right? Like which pallet is the person actually talking about? And then if you're supposed to pick it up, or you're supposed to drive past it, you're supposed to keep track of it, then you have to figure out what to do with it. So identifying an object classification is just one piece of this problem. It's been called the symbol grounding problem, this idea of mapping between words and symbols. And there's a paper that came out in 1990 that sort of introduced this term. And a lot of people have sort of used it since then, this idea of grounding symbols to stuff that's out there in the world. And the other thing is we don't just want to, like the power of a natural language interface isn't just following commands. We'd also like so sort of the difference between the idea of having a fixed vocabulary, that would be a lot easier, right? Like if we just decided that there's 5 commands we want a robot to understand, we could do it. We could make a speech recognition system, we could use our classifier to figure out which of those 5 commands were, and then we could map that to some pre-baked policy. And it would work. Like we would have a robot that responded to voice input. But what I was really interested in is commands that are produced by untrained users. So here's some examples of these commands. We collected them from people on the internet. And they're all telling the robot to do this action. That's on repeat in this video here, so it's going to start again in a second. So it's holding a pallet right now. This is the start. It lifts it up. It drives forward a little bit. It puts it on the flatbed. And then it drives back a little bit. And we asked people to look at this video and said, how would you command an expert human operator if you wanted them to do this? If you wanted them to carry out the action that you're seeing in this video. And that's all we told them. So it's all the same task, but you can see that they say they do things in very complex ways. So they sometimes say place, or lift, or arrange, or load, or put. They talk about this palette in different ways. So sometimes it's the palette of tires, sometimes it's the tire palette, sometimes it's just tire palette, they drop the determiner. They misspell tires up there, they call it second palette of tires. Some people from AMT aren't always from the US, so that's probably a legitimate spelling in, I think, British English that we're seeing there. And they say where it's supposed to go in different ways. So on the trailer, next to the other skid of tires, next to the pallet of tires that is already loaded on the trailer, unoccupied location on truck, with no determiners again. So there's and the other thing that they do that's challenging is they break this down in very different ways. So somebody said something very succinct, put the tire pallet on the trailer. Very short, one version. Other people gave much longer commands. So here they said, they broke it down into smaller chunks. They said, lift tire pallet, move to unoccupied location on truck, lower tire pallet, reverse to starting location, lower forks, end. So they're kind of maybe making up their own version of a programming language or something to talk to this robot. But you can understand it, right? Like if you were driving this forklift, for most of these commands, you'd probably be able to figure out what to do. And you do something reasonably close to what you're seeing in the video. And so what I'm going to talk about today is one way that we can make a computer, an AI algorithm, understand some of these same types of natural language commands using the techniques that we've talked about in the class. So I'm using search, using probabilistic graphical models, and machine learning and inference to make this happen. So the final thing we want to do, or I want to do, one of the great things about doing research is it's like you get to do what you want to do, like what you think is interesting, and not what anybody else is telling you is interesting. It helps if other people think it's interesting too, because then you get like papers and funding and all those kinds of things. But fundamentally, you get to do what you think is cool. And one thing that I think is really cool and also very important for language understanding, and one reason why it works so well for us, is that we're not just stuck with this one command. So like, if you were in this environment and there was, a couple of trucks in the environment, and you weren't sure which one they were talking about, what would you do?
Ask them which truck.
You'd ask them, yeah, you would ask a question, you would have dialogue, okay? So you say something like, which truck, and then the person's gonna say that one, it's another doing gesture recognition, or they're gonna say the truck over in receiving, or something like that. They're gonna give you more information in order to enable you to correctly follow the request that they're asking you to do. So what this looks like is again, it's like a POMDP or an MDP. There's some unknown state in their brain of what they want you to do. And you're trying to figure out what it is, and they've given you an observation of the environment. They've told you something. And you're trying to figure out, like, is that enough information that I should just take an action? If I'm going to maximize if my utility is maximized by doing what they want, should I just take an action? Or should I ask questions? Should I ask lots of questions? How many questions should I ask? If I ask lots of questions, it might be really annoying. So maybe there's a cost to asking a question, but not as big of a cost as doing the wrong thing. So you can sort of imagine defining an MDP or a POMDP in this space. And actually, when people, so who's ever called up to order airline tickets or tech support for your Comcast, and you've gotten one of those automatic dialogue units? Who's ever done that? And it starts talking to you, right? And you say things, and it tries to route you to the right place. Who liked it? Yeah, not very many. So the way those work is using POMDPs. There's actually a very recent review paper that came out sort of surveying the last 5 or 10 years of this research, and basically saying now the right way to do dialogue system, the standard way to do dialogue systems is with POMDP, where you define usually it happens when you have like the Comcast scenario or the airplane ticket scenario, where there's a very fixed tree of things you could need, and you can never jump out of that tree. So the state space, the underlying state space, is small and known to the designer, to the system at the beginning, and then it'll do some kind of naive Bayesian kind of thing with bags of words assumptions, where it's counting up the words that you're saying and figuring out from that what state you're likely to be in, where the real state is like what you want to have happen, like, them to cancel the extra fee that they charge or something like that, or book the ticket that you want to have booked. And that's how these systems typically work. It's not in robotics. What's happening now in robotics, so sort of one of the very cutting edge of what we're doing in my lab right now is trying to think about how these systems can work for a robot where you don't necessarily, you might know something about what's in the environment, you don't necessarily know the exact state of the world in advance at design time. You might get objects, you might get unexpected requests, and you want the robot to be able to operate anyway, do the right thing anyway, even if all of that stuff isn't baked into the system at design. So the sort of different things we're going to talk about is sort of what I think about a lot is how can we make robots understand natural language. So following instructions we've already talked about, so things like put the metal crate on the truck. Asking questions when it gets confused. What does the metal crate refer to, or which truck? Also, I think I've already talked about this in an earlier lecture, making robots that can understand what people are telling them about the environment. So things like the metal crate is in receiving. And then finally, this is some of our newest work, asking for help. This paper actually just got in last week to a robotics conference. I'm really excited about it. So the idea is the robot gets stuck, and it's going to ask a person something like, please hand me the black leg that's under the table. And the person's going to have to try to do it. And the idea is, like, if you're an expert robot operator, if you made that robot, you probably don't need to say anything. You can kind of look at it, look at your debug consoles, put some print statements in there, restart a few things, and then it'll kind of work. But if you're not the designer of the robot, you don't really know what's going on. You're not able to take those kinds of actions to fix things. So the idea behind this work was to make the robot say what it needed using words so that an untrained person could figure out what to do so it could continue operating autonomously. All right, so related work is actually interesting because it surveys different approaches people have taken to this problem. So the sort of oldest models, which people call GoFi, good old-fashioned AI. That's an acronym you can Google. It's sort of symbolic approaches. And the idea is that, so like this Winograd 1970 was done during the founding years of AI. At MIT, Marvin Minsky was the thesis supervisor, our own Eugene Charniak and Jerry Sussman, and Terry Winograd is the sort of thesis guy, first author for the thesis, the guy who sort of led the project. Made the system which understood natural language commands in Block's world. It's called Assured Loop. And the way that it worked is they spent a long time programming different word meanings and models for parsing those word meanings. They didn't use statistical approaches. They didn't use learning. They just used a lot of time and energy making this whole thing happen. And it actually, if you go look at the sample dialogue behind it, like of the things it could do, and you can also like run. There's versions of it you can still try to run and play with. It's amazing. Like the types of things that it can understand. It could you understand complex commands like pick up the smallest blue block, and it would do it, and it would move other blocks out of the way if it needed to in order to pick up the smallest blue block. You could define new terms. You could define a pyramid as a square block with a triangle on top, and then afterwards you could say make a pyramid, and it would sort of do these kinds of things. It could ask questions when things were ambiguous, and it could explain why it had done something. So if it said, why did you move the red block? It'll be like, well, I had to move the red block to pick up the blue block, and you asked me to pick up the blue block. That sort of explains its own behavior. The challenge behind these approaches is when you sort of scale it up to the language that we see from untrained users. So if it was Terry Winograd talking to the system, there was lots and lots of things it could understand. But if you walk into it and start trying sort of random things, it was very easy to get stuck, to find, if you drop a determiner, it doesn't work. If you don't put a period in short loop, it doesn't work. There's sort of a lot of these edge cases where things just break down. So increasing robustness was sort of what people struggled with in reaction to this work. And what they did in response is they sort of turned to statistical methods. So that you guys made this deny Bayes spam filter, right, where you didn't really parse anything, right? You needed bigrams and trigrams, you didn't parse the sentences. You didn't try to model, is this email actually asking you to buy Viagra, and if so, for how much money, and is the like you didn't do any of that. You just counted up how many words there were, and that gave you a distribution over whether it was spam or whether it was ham. And these kind of probabilistic methods are to do grounding work in kind of the same way. So grounding again similar between language and stuff that's in the world. And there's a long and venerable history in computational linguistics. Eugene's reaction to frustration with this early work was to go very strongly in the direction of probabilistic methods and probabilistic generative models. And he sometimes gets angry when we talk about the undergrad work and doesn't see the value in it that I think is actually there. Okay. There's also we talked already, I think, about Bronabon's work. This is even more recent. Kind of going back to the symbolic approach, which was integrating, what was interesting about it was integrating language and planning. So these approaches tend to have a very direct mapping between words. One word equals one sentence, one clause, one chunk of text equals one action. This is very low-level mapping to make that happen. And Bronabon's work and some of the other papers in this area, they're learning language through action. So we talked about Bronabon's paper at the beginning of the semester, where it was interpreting language as in terms of this reinforcement learning problem, and trying to take actions and then seeing how all these actions matched natural language descriptions. But what this work wasn't doing was modeling the compositional structure of language. So there's this kind of parsed tree structure, which maybe we didn't really talk about it in the course. How many of you guys know what parsed tree is? Let's say most of you. Okay, so I'll do a quick kind of tutorial on it. Like if you say the palette, the sentence has a structure, a tree-like structure, right? So like this chunk and this chunk are somehow separate. I could say pick up the palette, I could say pick up the barrel, I could say pick up the chair, I could say pick up the marker, and you understand all of those things, and it's all picking something up. Similarly, I could say pick up the palette, I could say kick the palette, I could say drive next to the palette, I could say go in circles around the palette, so I could take a picture of the palette. And again, it's all the palette, and the verb is different, and I'm sort of changing the action that I'm doing, but it's all the same words, all the same objects. So this structure you can sort of draw as a tree. This is called a noun phrase, this is a verb phrase, and then they are related by having a sentence, right? And as you get more complicated and longer sentences, there's more nodes in your tree. And this is what linguists study. So if you go over to CLPS, that's one of their questions, like what tree structures should be associated with these sentences, and how does it change across different languages? So these Bayesian models, where they're called bag of words models, where you don't use any of the parse structure. They're ignoring all of that structure, but it seems like a bad idea. Like there's useful information that's contained in that tree structure. So for example, if I say to the forklift, pick up the tire pallet near the ammo pallet, how do I know, if I'm just using bag of words, it's not going to know whether it should pick up the tire pallet or the ammo pallet. Like they're both there in the sentence. And there's no way to know that one is the one it's supposed to pick up and one is just a sort of locator expression, right? Whereas the parse tree kind of tells you, well, there's this, there's a preposition, it's augmenting the noun phrase, so near the ammo pallet is attached to the tire pallet, so the thing you're supposed to pick up is the tire pallet. That kind of syntactic information is telling people what object is to pick up and which object you're not. So the approach I'm going to talk about is called generalized grounding graphs, and the idea is to incorporate this parse structure and hierarchical information into the algorithm so that it's able to learn word meanings in terms of perceptual features and kind of get the best of both worlds. So you get the benefits of modeling the structure of language and having some knowledge of syntax, but you also get the robustness associated with machine learning and the ability to learn from large data sets so that you can let your model fit itself to the data instead of having to manually program everything. Okay. Any questions so far? Okay, so the next thing I want to talk about is how this whole thing works. So how can we learn word meanings? So the approach that we took to learn word meanings is we gave our system, we sort of framed it as a machine learning problem. So we gave our system examples of the robot doing something. So this is a video of the robot doing something. But paired with this video, we actually know a lot more. We don't actually have to do computer vision to know what's going on in the video because we have the log of what the robot was doing in terms of its own self-model. We know what objects it saw in the environment. We know what motor commands it sent to its motors. We know where it thought the truck is and where it thought the pallet was. So paired with this video, we're going to give it words in an unknown language. Okay. So this is an example of a. Does anybody know Polish? Okay. My husband is Polish. So this is Polish. This is a sort of Polish command of say put the tire pot on the truck. Put the pallet on the truck. To give you a sense of what the learning problem actually looks like for our system. So it sees these words in unknown language, and it's going to try to figure out how these words map to stuff that's there in the environment. It doesn't just see one example of this, it sees lots of examples. So here's a bunch of different videos showing the robot doing things and a bunch of different glosses in the unknown language. So I do my work in English because it's more mainstream. However, I think it's really instructive to look at it from this examples of the training data from this perspective. So it really gives you a sense of how hard the problem is to try to kind of map these different words. Some of those are cognates, working not, but you know, some of them aren't. Most of them aren't. So it's hard to figure out what's going on. Okay, so we're going to frame this problem in terms of inferring a utility function for the robot. So if you have words like go to the truck, we're trying to figure out what should the robot do. And there's lots of different things that it could do. And we want to figure out which one is better and which one is worse. Like the sort of searching versus scoring dichotomy that we talked about at the beginning of class. So what we're going to do is define an objective function, search for the action that maximizes the function, and then go off and execute that action. So our function here is just f. Our gamma 1 is the action. And we're going to just search over all the different actions and find a good one. Now, of course, there's an infinite number of these actions, and that might be a problem. But you can imagine in some kind of sampling way, we're just going to somehow pull actions from the world in some unspecified way. And hopefully it's small enough that we can search attractively to figure out what to do. So you see different actions like driving here, you give it a score of 0.99. Another one gives a score of 0.41. You get a whole bunch of these guys with different scores. And then you take the button with the max, and that's the one that you do. Okay. So as long as we have a decent space of these gammas, what we've done is sort of converted this question into how can we define our function. So that's sort of the essence of how this is going to work. And the way that we're going to do this is using machine learning. So we're going to learn it from labeled examples. So sort of switching to the probabilistic notation, our function is going to be the probability that this action is the right action, given the words that the person said. That's sort of probabilistically what we want. And then we're going to use that function to do this argmax to make it happen. And to learn this function, we're going to put on our standard machine learning test. So we're going to give it some positive examples and some negative examples, and then we're going to do standard machine learning. So you have your training set, go to the truck, don't go to the truck. We're going to have features, and I spent a lot of late nights thinking these features. So this magical feature vector that somehow enables the system to look at a trajectory and compute features that describe it for the machine learning algorithm. So things like whether the trajectory ends near the truck, and whether the trajectory, how long the trajectory is relative to the straight line trajectory that ends at that same location. How far away the trajectory is from your start point. So sort of lots of these different types of features. And then you can pick your favorite algorithms to optimize the feature weights, SVMs or log linear models or some kind of base, whatever you want. And you get this function. So what this looks like when we do this, I'm going to render this as a heat map. So you're going to have each pixel in the heat map is going to correspond to the probability value according to this function. Where red is high probability and blue is low probability. So kind of making each row, each column, I guess, in an image is going to be a pixel colored according to the probability that this trajectory that starts with this guy and ends at that pixel corresponds to go to the truck. And here it is. What do you think? Yeah, kind of nodding. So what do you like about it?
The reddest part's near the truck.
Yeah, the reddest parts are near the truck. So the trajectories that start here and end near the truck, it's giving a high score to. And it's giving low scores to other places, lower scores. What don't you like about it?
There are parts that, like in the upper part that are orangish or sort of red.
Yeah, something's
the
kind of
truck.
weird going on, because you're like, why would you want to do that? Like, it's really like to see everything be uniformly blue except for the ones that end near the truck. But it kind of looks reasonable, right? Like, it's not crazy. It's kind of okay. So this was, and this is an actual model that we trained using our Turker data. And I think the reason it's noisy is a couple of reasons. One is not enough data. I have my machine learning fixes, right? One is not enough data. Second is not good features. And third is not a good model. So we actually had, as a class project for that a couple of undergrads did last semester. One of them was your TA, Miles Eldon, was doing this. They tried a different machine learning algorithm. They tried random forests. And it turned out that random forests worked a lot better. The heat maps looked much, much better than the heat map here. I always thought it was like not enough data. But I was wrong. Like if they switched to a different algorithm, they got much better performance with much fewer weird things like this. Okay, so this is sort of go to the truck. What else is wrong with this sort of setup? Like a higher level kind of thing that might be bothering you. Can't see you.
Doesn't find the truck.
Yeah, like so what if I said go to the pallet? What's it gonna do? Or what if there was two trucks or something like? Is that gonna work? Is there anything, do we see anything about how we're gonna handle that? Yeah.
If you have a training set where it has labeled those words with the right adjective,
Yeah.
or then it will do the right thing.
Right, exactly. But we haven't said anything about it yet. So right now where we are is like you can imagine that you'd want to be able to handle things like go to the pallet or pick up, I guess you would want to pick up the truck, but like, you know, go away from the truck or something, or load the pallet on the truck. And you'd like to be able to understand these sort of other types of commands. And maybe we need like training data and stuff to do that. And that's sort of what I'll talk about next. Is like how can we expand this framework to handle these more complicated expressions. So mathematically what this looks like is you say go to the truck, but like what if instead they said go to the pallet? So what can we do to augment this to handle that situation? Yeah.
You have training data label where it has gone to the palette before.
Yeah, but before we get to how we learn it, what like sort of step 0 is what inference procedure are we going to need to run here to do this? Yeah.
If you do like the sentence trees, you can separate out like the action from whatever object you're going to.
Right. So is it okay to just argmax over the action, or do I need to argmax over other stuff too?
Other stuff too.
Other stuff too. Yeah, I had to argmax over the pallet or the truck. So what that looks like is that I'm going to stick a second variable in my optimization. And if I sort of make it most general, if I look at the commands that people produce, as you guys are saying, there might be a lot of other stuff. So mathematically, there's going to be n other things. And they're called gammas for grounding. So again, going back to this word, the symbol grounding problem. So they're object places, paths, and events in the external world. Question?
With these gammas, are we just treating this like a bag of words model, or is there also grammar and syntax and text as well?
What do you think?
It seems like not so much, because when you went from, when you went to two of them for go to the palette,
Yep.
you did like one represents go to and one
Yeah.
represents the palette, but
Yeah.
you have one actually represents the palette.
Yeah. So how are they related? Like let's just take go to the truck. Have we? I mean, from a sort of Jamesian perspective, right? with this probabilistic expression? Are they independent of each other?
No.
No, they're probably not. We could assume they are, but we haven't made any assumptions. We're just going to estimate the joint. So they could be related, and we probably want them to be related, right? Because otherwise, you might go to the chair and you completely ignore the palette if they're not related. Yeah, so you want them to be related. I've sort of already talked about the search space, so like you discretize this to make it small and fast. So we can just use breadth first search, or beam search, to search. And then the question comes back to the point that you were raising. So if we've got some kind of argmax over these n gamma variables, the question is, how do we get this model? How do we train it in a way where we can have a model for each one of these gamma factors in a way that respects the structure of language? So the idea is that we're going to factor this model. We're not going to make complete and total independence assumptions, because that's going to break things. But there are some independence assumptions that we can make that follow from the structure of the language. So we sort of already talked about this. So like what you like is if you say put the pen on the truck and go to the truck at training time, at test time, we should be able to use those same words in a new sentence and be able to understand it, even though it's never seen this sentence before at all, right? So the way that we factor is going to enable this to happen. So here's sort of what it looks like. We have this big model of all these gammas given the language, and we're going to write it as a product of factors, where there's a factor for each linguistic constituent according to the parse tree. So we'll read this factorization off the parse tree. Here, it's not actually like the parse tree isn't in this product explicitly, but the specific factors that we'll create will come from the parse tree. And each factor is going to get to look at that constituent and a subset of these groundings that are associated with that factor. So the way this is easiest to see, I think, with an example. So if you have the truck, the graphical model, and this is represented as a factor graph. So I think we talked about factor graphs really briefly. There's sort of undirected models and directed models. The most general way to write down a graphical model is something called a factor graph. So here you have, this is an example of one, where I have two variables and one factor. So these square nodes correspond to factors. There's some function of this variable and this variable. And I could have more factors. So the reason it's the most general way is because if I wanted to, I could have two factors here connecting these two. So let's say this is x and this is y, and I could also have a single factor. So that might be saying p of x, y equals p equals, not p instead of p because they don't have to normalize, f1 of x times f2 of x and y times f3 of x and y. And I want to know. Does that make sense? Why that's kind of, I can just make up whatever factorization I want and write it down as a factor graph with multiple different factors between the two nodes. Is that everybody okay with that? Okay. So for the truck, the words are the truck. The linguistic structure there is it's just one noun phrase. So our factor graph just has one factor with the words for the truck and the random variable gamma1 for the object. And it's supposed to be, it's supposed to be happy if it's a truck, a high value of this factor if it's a truck, and a low value otherwise. If gamma1 is an actual truck, and a low value otherwise. Similarly, if we have a more complicated expression, so on the truck, so we added one more word on the truck. So now it's a prepositional phrase. There's a preposition which is on, and the argument is the truck. So because there's two constituents in the parse tree, there's going to be two factors here. There's going to be one factor for the truck, which is exactly the same as before. There's no changes to it at all. And then a second factor for on. So this gamma2 variable, which we've introduced, is going to range over different places in the environment. So it might be here, it might be here. And it's going to have high values if gamma2 is on top of gamma1, and low values otherwise. It's not going to care about whether gamma1 is a truck or not, this factor here. It's only responsible for one. Just like this factor is only responsible for the truck. So the independence assumptions correspond to the linguistic sort of independence assumptions in the parse tree. And so what that lets us do is represent, convert linguistic compositionality, the way these word meanings combine in sentences to create meaning, as multiplication in our graphical model. So we can sort of do this with more complicated commands. So here's put the palette on the truck. This is sort of writing out the factorization. This is the factor graph. So this on the truck bit is the same. And then we have an extra variable for the action and an extra variable for the palette is supposed to be moving. If I look at go to the palette on the truck, here the PP, for put the palette on the truck, it's a 2-argument verb. We have put the palette, argument 1, on the truck, argument 2. So both of these factors for the palette and the truck connect directly to the put factor. For go to the palette on the truck, it's a 1-argument sort of verb / PP phrase. And so this noun phrase here, this on the truck here, gets attached to the palette. It doesn't actually talk to the verb. These different syntactic structures lead to different graphical structures. So now, sort of going back to your question, once we have this factor structure, it's a lot easier to train the model because we can explicitly build models for each of these factors separately by having positive and negative examples for each of these words. And then this model tells us how we can multiply or combine the individual word meanings together to get the function for the entire sentence. So to do this, we sort of, I already talked about this data that we got. We showed people these videos and we collected a data set and turned our machine learning crank and got these types of heat maps, which we could multiply together to get word meaning. So to see how well it worked, we again went back to Amazon Mechanical Turk. And we showed people videos. We did this in a simulation so we didn't have to make the real robot do all this stuff. We showed people videos of our system following commands and asked them, is the forklift that you see in this video executing the command pick up the tire pallet? Who thinks it is? Yeah, it is. And we showed them some where it was and some where it wasn't, and then some generated by our algorithm trying to follow natural language commands. So here's what it does. So the first two are sort of calibrating our triggers. We showed them known correct commands. We showed them the command, the original video that somebody else saw when they were generating the command. And 91% of the time they thought yes, it's correct. And then we showed them the command paired with some other video that wasn't the one that somebody saw when they generated the command. And most of the time, 100% of the time, they said no. And then we tried it with our system in different configurations. And the sort of takeaway from this is if we run it as ground truth parses on the whole data set, we actually do pretty badly on a sort of absolute scale. We get about half of them right. But it's actually encouraging when you compare it to using a random cost function where we don't try to incorporate information from language at all. We see a significant improvement. And if we look at the ones where we think we got right, the sort of top 30 most confident ones, then we get 63% of them correct. So it's not great. This is not something that's ready to run on your PR2 at home. On the other hand, it's kind of cool because it's demonstrating that it's possible to make a robot that can learn language from crowdsourcing on the internet and sort of incorporate a compositional structure of language into its inference to understand very challenging commands that are produced by untrained users. And so the sort of end of all robotics talk shows you it running on the real robot. So this is me talking to the robot. I'm using a precondition system running on the microphone, on a headset microphone. And from when I started talking to when it started moving is how long it takes to do the inference. So here you're going to see the pickup subroutine running. So it's going to speed up in a second. It's going to move its fork up and down to scan to see where the pallet actually is, and then do a secondary scan, and then pick it up, tilt it back, and then drive over to the truck, and then lift it up, drive forward, and put it down on top of the truck. All using word models trained by the truckers. Okay, so that's sort of understanding commands. Any questions about any of that so far? Yeah.
How do you actually generate the parse tree without prior knowledge of the language?
We use the Stanford parser to do that. So there's a lot of work in computational linguistics creating parsers, essentially. Typically trained on the Penn tree bank, which mostly consists of the Wall Street Journal articles. And it actually works kind of okay on a lot of commands. We would have problems because, like, if you'd say, like, we were doing work where, with indoor robots, and we would say things like, go down the hall, and it hates for down to be a preposition. It wants down to be an adverb because the market's down today. So we would definitely get errors in parsing due to things like that. We usually in my papers we'll run it with manually annotated parsers as well as a sort of off-the-shelf automatic parser. And typically you'll see about a 10 to 15% improvement from using ground truth parsing. So parsing helps, but it's not like I don't know, 10 or 15% was enough to make me feel like it's good enough for government work. And it's not the key thing that's blocking us. Most of the people I talk to, like Eugene, thinks that we could get much, much better parsing if we annotated our own data from our own robotic domains. Then it wouldn't think the market is down, it would think down the hall. And the other thing it doesn't like very much is these imperative commands. Because you don't see, like the Wall Street Journal doesn't usually tell you to do things. So all the time it'll try to find any excuse it can to think that these are nouns, these initial verbs. So that's another common problem that we saw. And again, I think it's just related to the training data. The other problem, of course, is ungrammatical sentences. So the Wall Street Journal tends to be pretty grammatical, whereas our Turkers don't always follow those rules. As you saw, they were dropping determiners and stuff like that, and that'll also mess up the parser. If there's no the, it really won't always know to make a noun phrase there and stuff. Any other questions?
How many training sentences for this particular task?
This was trained and tested on about 280 sentences, and I think we had like a 70-30 training test split.
And how many parse trees are there for those 200 they use?
How many parse trees?
Yeah, right.
Well, each sentence has one correct parse. I'm sort of quoting because maybe the person hadn't, there's often multiple parses that are associated with a sentence, and it's sometimes hard to know which is the one intended by the person, but you can sort of, as a working assumption, decide to say that each sentence has one correct parse.
So you have like more than 200 different parser models for this problem.
Yes, exactly. Yeah, so that was the new thing about this work that hadn't been done before. So in our class, when we had a graphical model for particle filtering, like we were making new variables and every time stuff, right? Like we were sort of making this Markov assumption, and we got to see the new observation and the new state and our new update. But it was a very symmetric structure. And in some of our simpler problems, like like for the spam filtering, we had one model, right? We had the class, we had the bag of words, and there could have been a lot of words, but once you trained your model, you knew for sure how many factors you had, how many random variables you had for your feature vectors. In this work, we didn't know that. So sort of like we did for particle filtering, where we defined a systematic way to make a model after you got a new observation, like a systematic way that you created new factors based on observing a new x, observing a new, observing a new z, a control, a new mu, and then estimating our state from those factors. The contribution of this work was to say, well, here's a systematic way to make a model for a natural language command when you've got the parse tree. Here's how you can train it, and here's how you can combine those factors to make it do cool stuff. Okay. More questions, or should we go on? Okay, let's go on. So this is some example commands from our data set, where they said, move the pallet from the truck, or remove the pallet from the back of the truck. So what do you notice about, let's say, this command in this environment? If you were trying to do this command, what would you do? Yeah.
It's not very clear, like what you finish with.
There's two pallets on the truck, right? Right. So it's not. Is that what you were?
Or like once you take it off, what do you do with it?
Right. Okay. So that's true. Like once you've taken it off the truck, what do you do next? Where should you put it? Let's just say that maybe they'll tell you another command when that happens. So you're just trying to do this command: move the pallet from the truck. What's in the scene? What's complicated about it?
There's 2 pallets.
There's 2 pallets. Yes, there's 2 pallets on the truck, and you're not clear, just knowing this information, which one you're talking about. So what about these? So I'll highlight. So what about these other 2? Offload the metal crate from the truck, or pick up the silver container from the truck bag. Yeah.
On the first one, you'd have to know that the crate is metal, and
Yeah.
the second one, you'd have to know what the color silver is.
Right, exactly. So maybe you know that. Like maybe you've got a model for that, or maybe Pedro gave you a classifier and it works really well. But maybe you don't. So even if it's not confusing to a person, there's lots and lots of reasons why it might still be confusing to the robot. Maybe the sun is extra bright that day, it's shining right into your camera, and you just can't see anything right now. You really might not, or maybe you've never seen metal in your training data. One of my annotators, one of my Turkers, said in our test set from before, they said, pick up the lonely palette. So, you see that, you're like, well, you look at the scene, you're like, there's a palette, it's all by itself. It is lonely, like, it's clear, like, it's obvious what one they're talking about. Like, it was very accurate. But our robot, like, that was the only person who chose to use that word lonely, and it was just not in our training data. Like, it was only in our test set, and it got it wrong. It picked up the wrong palette. So there's lots of reasons. Question? What's that?
No.
Okay. So there's lots of reasons why this could go wrong. Even if a person might be able to understand it. And besides that, even people, there's no way to understand. Like, people skip those commands. So what we did to address this is made our robot ask questions when it's confused. And what I call this information theoretic human robot dialogue. And what it was doing was leveraging the idea behind having a graphical model that had random variables corresponding to different parts of the command to make our robot intelligently select questions based on its self-model of what was going on. So what we would do is if you said offload the metal crate from the truck, and there was no metal in its training data, let's say, then it would have a uniform distribution over what pallet was being talked about. Like they're both crates, they're both on the truck, but I don't know which one is metal and which one is not. So it detects the entropy of this distribution, and then it asks a question: what does the metal crate refer to? And then the person says something like the box pallet near the ammo pallet, and then it doesn't update. So it sort of incorporates this new information and updates its belief over what object is being referred to. So this is a lot like your particle filter, in the way that we get an observation, we take an action, we get a new observation. It's a lot like a POM-DP. But what's different about the way we made this work is how we hooked it up to the compositional structure of language. We didn't just use a backup words model to do this. So we basically used this G-cube thing to model word meanings, and then we defined a metric based on entropy to select what to ask about. So if you're in an environment where they say put the pallet on the truck, and there's 2 trucks and 1 pallet, what should the robot do? It's going to ask a question. What should it ask about? Yeah.
Which truck?
Yeah, which truck? What does a truck refer to? What about this environment? There's 1 truck and there's 2 pallets. Same word, same robot, same program. What should it do? Which pallet? Yeah. So you don't want the robot to ask about everything, because that would be really annoying. You might as well just get your PlayStation controller out, or get behind the wheel and drive the forklift yourself. We want our robot to intelligently ask questions based on what's confusing right now in this command that the person said and this environment. So the way that we did this is we looked at the marginal entropy of random variables in our graphical model. So we didn't really talk very much about entropy. So who's heard of entropy? Okay. Anybody want to say what entropy is? What is entropy? Yeah?
It's a amount of disorder in the system?
Yeah, it's the amount of disorder in the system. It's how uniform versus peaky is your probability distribution. So if we go back to our slide from here. It's a way of measuring, so this distribution over two things, like which palette, where it's uniform has high entropy, and there's a formula for computing, for quantifying that Shannon came up with. And this is as low entropy, lower entropy, as it gets peakier and peakier and peakier, it gets lower and lower and lower. And entropy is a way of quantifying that. That's been well studied. It's used a lot for coding, encoding information, and messages and stuff like that. So basically, we searched through all the random variables, we computed the marginal entropy of that variable according to our probability distribution, which we could do because we had a probability distribution. And then picked the one that was the most confusing in that particular environment, and we asked about that. So we identified the thing that was the most confusing, and then asked about it. And that gives you exactly this behavior. So it'll decide this has high entropy in this scene, the truck has high entropy in this scene, and the palette has high entropy in this scene. Yes?
Would it always ask about the lowest, or would it have like a cutoff, like as long as they're all about this?
Yeah, so what we did in this paper is we had a cutoff. So when I talk about I don't know if I'll have time to talk about the evaluation, because we're almost out of time. When we evaluated, we basically did it by saying, let's ask one question and pick the best question. So first of all, let's ask 0 questions and see how accurate it is. Then ask 1 question, see how accurate it is. Then ask 2 questions, see how accurate it is. Then ask all the questions you could ask. And we showed that as you ask more and more questions, it gets better. But if you ask the entropy maximizing questions, you get better faster than if you just pick a question from the space of questions randomly. And we got it working for yes/no questions and these what do you mean by questions. Yes?
Does it update the graphical model after you
Yeah.
answer the question? Because it seems like,
Yes.
okay, but then it seems like if you say like the truck, you say, put the palette on the truck, and it's like, which truck? And you say, oh, that, the truck
Yes.
is this truck. Then it's going to learn that like always that is the truck.
Yeah, so here's what it does. I actually have slides for this. And Pratisha is an undergraduate. Robert was a super senior. He was like the year after he graduated. But she started working with me as a freshman. I like to have undergraduate like that. This is how we did it. We had a grounding graph for put the palette on the truck. Then you ask a question, you get an answer like the trailer near the boxes. And you get this other grounding graph. That's the same way, like you just read it off from the par structure. And then what we did is something called co-reference resolution. So you can, this is something a lot of people study. This is a textbook on computational linguistics. It has a whole section about it, where you can notice that the truck and the trailer near the boxes co-refer to the same object in the environment. And this is done a lot with like Wall Street Journal text. A lot of computational linguistics is like Wall Street Journal text. So like, President Obama delivered the State of the Union, the president said such and so, Obama had a fight with the Republicans, he did X, Y, and Z. So all those times I referred to Obama, I sometimes said President Obama, then I said Obama, then I said he, the president, and they all refer to the same thing. And co-reference resolution is basically saying, oh look, all of these different phrases are all the same entity in the environment. So that's what we did, and then here's the same kind of thing, the truck and the trailer near the boxes. So once we know that they refer to the same thing, it corresponds to a graph edit in the grounding graph. So we basically can take this variable and merge it. So you just have this factor and you have this new factor. And we rerun the same inference we ran to understand the original command in this augmented graph, and then ask a new question in that augmented graph. Okay, so we're almost out of time, so I will skip the evaluation. You can read the paper if you're interested. The high-level pattern for the evaluation was that asking questions improves performance. We had random questions and targeted questions, and asking targeted questions improves performance more than asking random questions. I'm going to skip this too because I think we already talked about it. I guess I just wanted to finish maybe by showing you this video, because it does help a lot of the work that's going on in my lab now. So this is making a robot that follows recipes. So it's going to make, I think it's going to make quick and easy sugar cookies. Yeah, quick and easy sugar cookies. So we downloaded this recipe from the internet, and we feed it into our system. We chunk it, and then we infer, or act in, this is, Daniela was the PI, the person who was behind the budget research. We send it out to the robot, and then we kind of, close the loop and actually make it follow the recipe. So here it goes. This is sped up 8 times. You can see the Kinect bouncing on its head to get the RGBD. Basically attach the spatula to the robot because you can't grip it tight enough to actually stir. And he spent a lot of time, Mario made the robot do all this stuff. And Mario spent a lot of time making that stirring algorithm work. So that it's compliant against the goal. This is showing the point cloud as it's doing stuff. And Stephen in the next class is going to talk about how you can make a robot plan these types of motions. Like forming things and bowls and stuff. So his group got to eat a lot of cookies this summer when he was doing this. Yes, it made a lot of messes too. That's why we had to put the protective layer on it so that it didn't damage itself. So Mario actually ran this system for over 40 hours. It takes about 2 hours to make cookies, end to end. And he ran this for like 40 or 50 hours over and over and over to quantify the failures that it encountered as it follows the recipe. So here it's later. All right, we're a little over, but at the end we basically get cookies. That's Mario. All right, guys. So I hope that was kind of fun. Dive into how the works.
I'm sorry. I'll do better next time. I'll do better next time. Are you going to?
What I manually and then it stays like hiding.
Yeah.
There's my email about
Yeah, I forwarded to Seth.
Of the Helix. Okay, so I'll talk to her about it then.
Yeah.
All right, great, thanks.
Yeah.
Can I ask you a quick question about the project?
Not right now. Sorry, I
No,
just gotta run
that's cool.
and do it.
That's cool. I'll just go